In this example, we're going to investigate the use of some of the scaling laws we've discussed in the lecture and also in the reading. And we're going to compare the scaling predictions to what we have from this pump performance plot. So let's go ahead and get started. We're told that we have a centrifugal pump tested at 3 different impeller diameters in a single casing. And the pump performance plot shows this. So we have the head rise versus volumetric flow rate for an impeller of 11 inch diameter, 12 and 13 inch diameter. So we actually have the data on this plot. And what we want to do is compare the results from this plot to what we would get from scaling. So here it says specify the flow rate and head produced by the pump at its best efficiency point with a 12-inch diameter impeller. Scale these data to predict the performance of the pump when tested with 11 and 13-inch impellers, and then comment on the accuracy of the scaling procedure. So let's go ahead and first of all just find the pump performance at its best efficiency point for the 12-inch impeller diameter. So for the 12-inch impeller diameter, we're going to be following that curve. The best efficiency point will be right there. That's the highest efficiency. You can see, we're at 86% efficiency here. And then if we look down here at the volumetric flow rate, and then over here at the let's see if I can do my best to draw this horizontally to find the head rise there. So when I did this previously and I was more careful, I got the volumetric flow rate at the best efficiency point for the 12-inch impeller diameter to be 2200 RPM. It's pretty close to what I had right there. I had the head rise for the 12-inch impeller best efficiency point as being 130 feet, which again is not too far off from what I estimated here. And then the efficiency, of course, at the best efficiency point for, let me write the 12-inch impeller best efficiency point as 86%. So that's what we get directly from the plot. Okay, now we're going to go ahead and use some scaling to predict what the volumetric flow rate and head rise will be for the 11 and 13-inch impellers. So the scaling rule that we derived in one of the lectures is that the volumetric flow rate at the new impeller diameter is the original volumetric flow rate multiplied by the new diameter divided by the old diameter raised to the cubic power. So for the 11-inch impeller, we can use our information here for, so D1 would be our 12-inch impeller diameter with Q1 being the 2200 gallons per minute. So it's just this data here. Here's our 2200. You know what? I just realized I wrote the wrong units here. This was 2200 gallons per minute, not RPM. Okay, so anyway, the 2200 gallons per minute for the 12-inch impeller diameter, that's the Q1 and the D1. The D2 is 11-inch impeller diameter. We use that formula, and you'll get the new volumetric flow rate as being 1690 gallons per minute. And we can also do it with a 13-inch impeller diameter. And for that one, you'd get the new flow rate as being 2800 gallons per minute. So that's what we predict from our scaling rule that we derived from dimensional analysis. And if you look at the plot up here, let me use a little different color. For the 11-inch impeller, which would be this one, our predicted volumetric flow rate, well, I mean, not our predicted, but if we look at the volumetric flow rate at the best efficiency point, which would be right about there, it's at about an 81% efficiency, it looks like. Let me go ahead and do my best to draw the lines there. So from the plot, I see that the volumetric flow rate for the 11-inch impeller appears to be about, looks like more like 2,000 gallons per minute from my plot. And then the head rise appears to be close to about, let's see, that's closer to 110 feet. That's this point right over here. So you can see our prediction of 1690 compared to 2000 is not great. It's not a great prediction. It's off by something like, I think I calculated it at 16%. So not a great prediction there. If we do it for the 13-inch impeller, let me go back up to the plot and show where that one is. So here's our 13-inch impeller. Our best efficiency point is right about there. And there's our volumetric flow rate. Looks like it's pretty close to about 2,500 gallons per minute. And then the head rise, when I draw that one in, it looks like just over 150. So let me write these down. So this was 2,500 gallons per minute. And this one, I got to be about 153 feet. That's just being a little more careful with my drawing my line. Actually, I shouldn't write 153 is a little too precise. I should just write 150. So anyway, comparing our predicted volumetric flow rate at 2,800 to the 2,500, you see, again, it's not great. It's not a great prediction. It's off by about 12%, I think, in this case. Gets us in the ballpark, but it's not ideal. There is a different kind of scaling. Remember, this one came from dimensional analysis. But one of the things in dimensional analysis is you assume that everything has perfect geometric similarity. But in fact, we don't maintain perfect geometric similarity here because we're putting a different sized impeller in the same sized casing. So we're violating geometric similarity. So there's an empirical scaling law that we talked about in lecture that seems to work a little bit better. So let me write what that empirical law looks like. That's just Q2 is Q1 times the diameter ratio squared rather than cubed. So this one doesn't come from dimensional analysis. It just comes from some empirical, it's an empirical correlation that seems to work pretty well. When we use that, our volumetric flow rate that we would expect for the 11-inch impeller, that comes out to be 1,850 gallons per minute. And then when we do it for the 13-inch impeller, that comes out to be 2,580 gallons per minute. So now when we compare these from the empirical correlation, you see we're actually closer. So from the dimensional analysis, we had 1,690 for the 11-inch impeller. The actual is 2,000, but our new empirical correlation is 1,850, so it's closer. So this works better than that. Okay, and then when we compare for the 13-inch impeller diameter, our dimensional analysis scaling gives us 2,800. The actual one is 2,500. But using the empirical one, we get 2,580. So that one's actually much closer. It's only, I think, a 3% error here and an 8% error here, whereas this one was off by something like 12%, and this one's off by 16%. So this scaling, based on just an empirical correlation, seems to work better than the dimensional analysis one. Okay? And the reason, again, for that is because the dimensional analysis one assumed perfect geometric similarity, when in fact there isn't. We know that because we're using a different impeller diameter but the same casing. All right, let's go ahead and see what happens if we scale the head rise. Okay, so for the head rise, from dimensional analysis, we'll get that H2 is equal to H1 times D2 over D1 squared. And again, if we go ahead and use the values for D1 being the 12-inch diameter and H1 being the 130 feet right up here. We got those from that from the plot. And we use that scaling rule. Then for the 11-inch impeller, oops, let me change my notation here. The head rise for the 11-inch impeller would come out to be 109 feet, and the head rise for the 13-inch impeller would come out to be 153 feet. And let's compare that to what you get from the plot. From the plot, we said the head rise for the 11-inch was actually 110 feet, so we're super close on that. And then for the 13-inch impeller from the plot, it was 150 feet. And again, we're super close on that. So the error for this dimensional analysis head rise prediction is very small. It's like less than 1 or 2%. So this works really well just by itself. So the volumetric flow rate dimensional analysis scaling is, it's not great. It's on the errors on the order of 10 to 20%. You're better off using the empirical correlation. That gets you closer. For the head rise prediction, the dimensional analysis approach actually works pretty well. So we can just stick with that one. Now, the last thing that we'll do is just make predictions for the efficiencies. Okay, so we had said that the best efficiency point for the 11-inch impeller is right here, and that appears to be about on the order like 81 or 82%. And then for the 13-inch impeller, it's right here. That might be something like 87%. Okay, so let's see what the predictions are for that. So there was an empirical formula for scaling the efficiencies. Looks like this. This comes from our notes talking about this topic. So that's, again, an empirical formula. Empirical just means based on experiments. So again, we had D1 was the 12-inch impeller. 801, the efficiency for one we said was 86% efficiency. So then when we combine these together, the efficiency that we would predict, the best efficiency for the 11-inch impeller would come out to be 86% also. And for the 13-inch impeller, we would also get about 86% when we plug in the numbers here. It doesn't change that much because this is raised to the 1/5 power. I'm just rounding these. And again, if we go back, so we predicted 86% for those 11 and 13-inch impellers using this empirical formula. And when we go back to the actual plot, for the 11-inch impeller, it's closer to maybe 81%. So we're off there a little bit. It's not too bad. And then for the 13-inch impeller, maybe it's around 87%. So that one's actually not too bad. It's pretty close. So that prediction down here for efficiencies is reasonable. It's not too far off. Okay, so anyway, I just wanted to show you how these scaling rules work and then just compare them to some actual data where we do know the performance at different impellers, just to have something to compare against. All right, we'll go ahead and end it there.